All right, well, good morning. We're going to try to do a quick little video talking about sequences and specifically what's meant by explicit notation versus recursive notation. This is an area that causes confusion quite often. So I'm going to walk through this problem and try to explain some of the basic ideas, and hopefully that'll help clarify things. So at this point, we have considered sequences, types of sequences. This one, -8, -2, 4, 10, -8, -2, 4, 10, and so on. This ends up, if you look at the pattern that's occurring, this one appears to be adding 6 every time. That has two names at this point. The book has called this the sequence generator. That's a general term for the pattern that's determining subsequent terms. It could be times something, it could be add something, it could be some other pattern. When this pattern, the sequence generator, is like this, where it's adding a constant amount, that means this is an arithmetic sequence. Arithmetic. That's the sequence type. You probably learned this from remember this from last year. This pattern leads to a linear graph. And since it's linear, then that brings in y equals mx plus b. We could write a rule for this sequence using y equals mx plus b. Now, this section is starting to talk about, okay, but there's more than one way to write a rule. And so the type of rule that you're probably familiar with is what's called an explicit rule. And it's the rule that would come from this for a linear. The difference being this type of rule would allow me to take the term number and use that to generate the term directly. You've got to visualize this sequence almost like a table. This is term 1, this is term 2, this is term 3, this is term 4. Well, I shouldn't say this. -8 is term 1, -2 is term 2, 4 is term 3, and so on. You've already been dealing with a whole bunch of new notation. Term 1 equals -8. Term 2 equals -2. So the number that goes inside the parentheses is the n, which is the term number. And then t of n takes the place of y. That's the actual term. So n is the term number in this context. The context is sequence. N is like the x in the rule. T of n is saying the actual term, term 1, the actual term is 8. So you got to think of t of n. You've got to think of t of n as the same thing as the y, and the n is the same thing as like the x. It's just different notation, and n and t of n are notation that are specific to the context of sequences. All right, so let me get back to what I was talking about over here. If you visualize this table, I know that you had a lot of practice last year writing rules for this type of sequence. We'd have to work backwards to term 0 to get the b. So the rule in y form would be 6x, and I'd have to go -6 to get -14 for term 0. So 6x minus 14 would be a rule in y equals mx plus b form. Well, that rule would take the term number x and give back the actual term value. But since we're in the context of a sequence, we're going to write it differently. The term, any term, t of n, so that takes place of y, is found by taking the term number and multiplying it by 6 and then subtract 14. So these two rules, they're the same rule, but we use t of n notation in the context of a sequence. This is called an explicit rule. Explicit means a rule, a function that allows me to take any term number use that rule to get the value of that term. So if I wanted to know T100, if I wanted to know the 100th term, I'd go 6 times 100 minus 14. So that way I don't have to add 6 repeatedly to get all the way out to the 100th term. So an explicit rule is a type that lets you calculate the value of any term just by substituting the term number into the rule. That's the type of rule that you spent a lot of time learning last year. Well, so the new thing in this section then is the idea of a recursive rule. And that's a rule where we're looking at the sequence like this, where it's adding repeatedly. So it's a new notation. It's a different way of looking at the sequence. Let me recopy the sequence because now we're going to look at it recursively. -8, -2, 4, 10. The next term would be the previous term plus 6. So now when we're writing a recursive rule, we're thinking left to right instead of input to output. So we're thinking this way. Oops, that's not what I wanted. Let me, oh well, we'll just live with it. +6, +6, +6. Thinking left to right, that's thinking recursively. And so now the other thing that they're introducing here is this idea. T of n plus, oh, let me erase that. I don't want that there. Let me see. Nope, that's not what I want either. Oh, I haven't used this in a long time. Can you tell? Eraser. Let me erase that. I'm going to move that. So T of n plus 1. So I'm going to look at this like, okay, currently I'm thinking about this term. That's the current term, the fourth term, but I'm currently thinking about that. So if I'm thinking about this term, how do I get the next term? So think of when you see T of n plus 1, think in your head next term. The next term equals, so if this is n plus 1, this is 5, term 4. If I'm thinking about term 4, then the next term would be term 5. So the next term, this is not coming out very well. I hope this isn't confusing. The next term equals the current term, the one I'm currently thinking about. So I'm going to think, when I see T of n, I'm going to think current term, the one I'm thinking about right now. This is what happens when you throw a video together without really thinking about it very well. The current term plus that common difference, that amount that it's growing by. So this is a rule that describes what's happening to the pattern. To get the next term, you take the current term and you add 6 to it. And you could do this forever. Okay, 16, 22, 28, 34. I could do that all the way out to any term I want, but it's not terribly efficient. So this is what's called a recursive rule. A recursive rule is one that allows me to get the next term by doing something to the current term. So in other words, a recursive sequence is thinking left to right, add 6, add 6, add 6, add 6, add 6, instead of thinking vertically. What do I do to the term number to get the term? Explicit's thinking from term number to term. Recursive's thinking from one term to the next, to the next, to the next. Now, there's a problem with this notation. This is describing any sequence that's adding 6. So this rule, as it stands, would also work for this sequence. This describes any sequence that's add 6 over and over again. So how do I specifically then go, okay, well, this rule is for this sequence. I have to add in to my notation the initial, well, not, yeah, the initial value. T of 1 equals -8. So now, if this is my rule, the next term equals the current term plus 6, and the first term is -8, that recursive notation now describes this sequence. If I wanted to describe a different sequence, suppose I wanted to describe that one that was 0, 6, 12, 18, ... Well, the next term equals the current term, add 6, but then in this case, term 1 is 0. So starts at 0, adds 6 over and over and over again. So that would be a recursive functional recursive rule for that sequence. Okay, so bottom line, explicit versus recursive. An explicit rule is really a more useful rule. It allows you to go from any term number directly to the term. This is the type of, I'm sorry, right here, from any term number to a term. This is the type of rule you spent a lot of time thinking about in Math 8. You just remember it in y equals mx plus b form instead. So it's different notation for the same thinking. The T of n notation tells us that the context we're talking about is a sequence. Earlier in the year, you had f of x notation. That is another notation, it's function notation that replaces y equals mx plus b. And so this could be used for other contexts. The new thing is the idea of recursive notation. And that's where we're thinking about, well, to get from one term to the next, I'm just adding 6. And so you're just saying the next term equals the current term plus 6. What if it's a sequence where it's not adding? This video is getting a little bit long, but let's do one more. So you also saw earlier, if you did the rabbit problem, you saw a sequence like this, where it's not adding a constant amount. This time, the generator is times by 2. Later in the chapter, you're going to learn a lot about how to write an explicit rule for this. The form, just to steal some of the aha, it's a times b to the x power. That's the y equals mx plus b for this type of sequence. This type of sequence where it's multiplying by the same amount over and over again is a geometric sequence. But what I wanted to look at was the recursive rule for this. The next term equals the current term, but what do I do to it? I times it by 2, so I'm actually going to move that. The next term equals 2 times the current term. That describes this pattern. To get the next term, I double the current term. To get the next term, I double the current term. And then I have to, because there's a lot of sequences that it's multiplied by 2. It could be 1, 2, 4, 8. There's a different sequence that fits this description. So I have to give an initial value. Term 1 equals 2. So that would be a recursive representation, a recursive rule for this sequence. All right, I'm going to call it quits there. Hopefully that gave you a little bit better understanding of what's this difference between explicit and recursive. All right, I hope that helped. Talk to you. Let me know if you have any questions, and I will talk to you soon.